Today's recap is going to be about volumetric analysis. Now that's the analytical technique that we use to determine concentrations of unknown solutions using known volumes of other solutions of known concentration. Now remember, volumetric analysis often involves titration, and there are two different types. We have our acid-base titrations and our redox titrations. So I strongly advise you to go and review all that content to make sure that you fully have that understanding and you can fully apply that to questions involving titrations and volumetric analysis. Let's talk about volumetric analysis, which, as its name suggests, is analysis via volume. So let's start with how it works. One of the most common ways of running a volumetric analysis is via titration, which is what we're going to go through now. First step in a titration is to pipette a known volume of solution of unknown concentration into a conical flask. So what we're intending to do is determine the concentration of a solution of unknown concentration by reacting it with a solution of a certain volume of a solution of known concentration. So we get our solution of unknown concentration and we pipette, say, 10 or 20 mils into a conical flask. The next step, we fill the burette, which is secured on a retort stand with boss head and clamp, nice and straight, and we fill that burette with a solution of known concentration so that we can deliver a very specific and accurate amount of solution into our conical flask to react with our unknown solution. If you're doing an acid-base titration, you're going to need to add a suitable indicator, which means a substance that will change colour once the reaction has finished. So if you're titrating hydrochloric acid and sodium hydroxide, you want an indicator that changes colour at as close to set pH 7 as possible. But we can also do redox titrations, which sometimes you don't need an indicator because the species being formed by the reaction that's occurring is a different colour to the original species. Our next step is to slowly add the solution of known concentration from the burette, watching very carefully for a colour change. And you need to make sure that you get right down to the very end and tiny drop by drop by drop by drop, because we need to be extremely accurate. So you add that solution into the conical flask until a colour change occurs from your original indicator colour or the colour of the species you're testing. And then finally, just like gravimetric analysis, you use your stoichiometry to determine the concentration of the unknown solution, using the volumes of what you delivered in the first step of your unknown concentration, and then using the volume you delivered from the burette and the concentration of that solution of known concentration. Again, as with all analytical techniques, there are some errors and limitations to be mindful of when you're conducting these kinds of experiments. So the first one is the accuracy of your precision glassware. So your precision glassware is your pipettes and burettes because they deliver very, very, very accurate amounts of solution. But they, like anything, they do come with a plus or minus amount of between 0.2 and 0.3 mils. You have this in your notes, so make sure you go and read up on that. You can also get some unreacted solution getting caught on the neck of your conical flask when it's dripping from the burette. So if that has been left the burette but hasn't reacted, that's going to have an effect on your final result, because it's going to say that more solution was needed than actually was needed to react. You always have to be mindful of the difference between equivalence and endpoints. Your equivalence point is your actual stoichiometric value figured out using your equation, and then your endpoint is the point at which the indicator changes colour, which can be slightly off because for it to go from one colour to the other, it's going to have slightly more of the other species of that next colour. A couple of common uses of volumetric analysis include the ethanoic acid content of vinegar, which you may have done in the past, and also what my class did was we determined the iron content of some lawn food. Now, some important things to remember about volumetric analysis is that you need to use a titration curve to choose an indicator for an acid-base titration. So you want your indicator to be changing colour as close to the equivalence point as possible, so that your endpoint and equivalence point are as close as they possibly can. You can also do redox titrations as well as acid-base titrations. And often your redox titration will not need an indicator because when the substance is reduced or oxidised, the actual colour of the species changes. For substances that are weak acids or bases, they are often analysed using a back titration, which means that it's not titrated straight away through this step. There's a few steps beforehand where that weak acid or base is reacted with another substance, and then the titration is conducted with the product of that reaction, and then you work backwards from there stoichiometrically to figure out the concentration of your weak acid or base. Always make sure when you're reading the burette you read down, not up, with your decimal places, and that you always read from the bottom of the meniscus. And also there's one more additional thing for you to remember, is that when you need to rinse your glassware before you use it with particular things. And the good way to remember it is the precision glassware, that needs to be rinsed with the solution to be put into it. So if you're putting 0.01 molar hydrochloric acid into the burette, then you need to rinse it with 0.01 molar hydrochloric acid before you use it. Same with the pipettes. The things that end in "et" need to be rinsed with the solution to be used. But things like the conical flask, it's not precision glassware, so it can just be rinsed with deionized water. Now we still need to rinse it with deionized water to make sure that there aren't any other compounds in there that are going to affect our results. And that's volumetric analysis recapped. Time for an example. This is a question from the 2009 exam on a volumetric analysis. So let's read the question. A student is to accurately determine the concentration of a solution of sodium hydrogen carbonate in a titration against a standard solution of hydrochloric acid. The first step in this experiment is to accurately dilute 100 ml of 1 molar hydrochloric acid solution to 0.1 molar solution using a 1 litre volumetric flask. So that's some very important information there. However, instead of using distilled water in the dilution, the student mistakenly adds 900 ml of 0.0222 molar sodium hydroxide solution. So what's happened here is the intention of the titration was to titrate hydrogen carbonate with hydrochloric acid. And what's happened is instead of diluting the hydrochloric acid solution with distilled water, he's used sodium hydroxide instead. So what's actually happening in our volumetric flask is there's a reaction happening, not just a dilution. So the first part is asking us to write an equation for the reaction that occurs in the 1 litre volumetric flask. So what we have in there already is our HCl, and it's a solution, so it's aqueous. And what is added is some sodium hydroxide, which is also solution. And we know in acid-base reactions, the acid is the hydrochloric acid and sodium hydroxide is the base. Acid plus base makes salt and water. So our salt is going to be sodium chloride as an aqueous solution plus our water, which is not a solution, it is. Okay, let's move on to the next part. Calculate the concentration of the hydrochloric acid in the 1 litre volumetric flask after the student added the sodium hydroxide solution. Give your answer to correct significant figures. The best way to approach this problem is to determine the number of moles of hydrochloric acid that would have reacted with the sodium hydroxide. And as you can see from our equation, the ratio is 1 to 1, so you just need to find the number of moles of HCl final by figuring out your number of moles of HCl initial and then taking away the number of moles of sodium hydroxide that was added. Since they're both solutions, we can use the N equals CV to determine their concentrations. So for our HCl initial, it would have been 1 molar is its concentration times its volume, which was 0.1 in litres, minus the concentration of our sodium hydroxide, which was 0.0222, times 0.9, because 900 mils was added, which should give us an answer of 0.0800. Question C requires you to think outside the box a little bit. So the student then uses this contaminated hydrochloric acid solution to determine the accurate concentration of the unknown sodium hydrocarbonate solution. Will the calculated concentration of sodium hydrogen carbonate solution be greater or smaller than the true value? Justify your answer. So you need to say higher or lower and why. So I would say that it will be higher, because it's going to take more of the hydrochloric acid solution to neutralise sodium hydrogen carbonate solution, as its concentration is lower. And to finish with, what would happen if Iron Man and the Silver Surfer teamed up? They'd be alloys! Thanks for watching.